Okay, so this is where I stopped in the previous video, and what we have done is to discretize the flux term in two steps. We use the central difference two times. First on F, so you have 1 over delta x times 1 over delta x times this difference. Then we write out what F is, which is everything in the parentheses, and discretize that also using central difference, and that gives you this and that, right? So to continue, what I'm going to do next is to discretize the right hand side, and you will later see in subsequent videos that there are different ways we can discretize this. We can use the forward difference, we can use the backward difference, which is usually referred to as the backward Euler scheme, and that's what we're going to use. So we're going to use the backward difference on this right now, and the term is, so this is the left hand side flux term. Now we're going to focus on the storage or accumulation term, and it's the time derivative of phi saturation, because it's multiphase, divided by BO, which we got by substituting rho S over, rho SC, density at standard conditions, divided by oil density at reservoir conditions. And that's brought in BO into the equation. And that's what we have right there. And we're going to use backward difference, so it's going to be 1 over delta T, right? And we will have phi S naught over B naught at, we can use n plus 1 to represent current time step, and n as the previous time step, so that's your backward. And all these other terms here will be at n plus 1 for an implicit scheme, and you will later see we have explicit schemes too, and they all vary by their stability, numeric stability. So this is what you have for the discretization of the right hand term. This is what you have for the discretization of the left hand term. So what we do next, so technically the equation is this discretized form equals this discretized form, but I want to do one calculation on top of this instead of just writing it as is. So multiply both sides, right? By volume, by cell volume, the volume of the cell, which is what? Delta X, delta Y, delta Z. So if you multiply this by delta X, delta Y, delta Z, what's going to happen to this? This is going to lose 1 delta X. And just in keeping with the form of the equation in your slides, I'm going to take out this one, right? And leave this one outside. And so this will have to be multiplied by volume, right? Which is delta X, delta Y, delta Z. So multiply both sides by this to obtain, then we equate the discretized form of the left, equate this to this. So it's going to be 1 over delta X KKR O mu O BO pi plus half. And now it's just pi plus 1 minus pi minus KKR O mu O BO at what? I minus half. Pi minus 1. This has gone away by multiplying by delta x, delta y, delta z. So you are left with delta x got cancelled, right? This delta x got cancelled, so you're left with delta y, delta z, which is area. Right, so this is area. You can actually just write area here. When you are flowing in the x direction, what's the area? This is the x direction. What's the area? It's going to be delta y, all right, times delta z. So it just works out, all right, by just multiplying by delta x, delta y, delta z. So this is really where area shows up, which is why I kept emphasizing that the areas in the previous continuous form was just multiplying both sides and keeping with however it was derived in the textbook. But really, we work without the area, because now you see area shows up on the left-hand side, but volume on the right-hand side. Why don't we have volume on the left-hand side? Because that volume has been divided through, or has been multiplied through by 1 over delta x, and the delta x goes out, leaving delta y, delta z. So area is delta y, delta z when you're flowing in the x direction. And what do you have here? It's going to be volume over delta t times this discretized storage term. Good. So that's your discretized form of the equation. And you can compare that with what you see in your slides, which is this right here.